direction you wish, to cross continents and oceans, to range over forests and deserts and mountains. All this birds have been able to do for 150 million years. But they weren't the first, or indeed the last, in the skies. We are setting out to explore one of the most astonishing stories in the natural world. The way in which animals manage to rise up from the surface of the earth and colonize the air. From the dazzling aerobatics of the insects to the majesty of ancient winged reptiles. The splendor and agility of birds. And the sonar-guided precision of night-flying bats. Flight has been the key to the success of some of our planet's most remarkable inhabitants. To analyze their spectacular skills, we will use the latest technology. And we will travel around the world. From the jungles of Borneo to the fossil-filled rocks of China and the cloud forests of Ecuador. We will take you into the air and travel with animals as they fly. Evidence for the very beginnings of this astonishing story can be found close to home in the fens of Cambridgeshire. Here live creatures that have an ancestry stretching back millions of years. Nobody knows exactly how the first flying animals in the world evolved, but there are creatures alive today that can take us back to those far distant, remarkable times. And they live, surprisingly, underwater. Looking down through the surface to the riverbed is like travelling back in time over 320 million years. It was then, in an age long before even the dinosaurs evolved, that creatures like this first appeared in the waters of the earth. It's an insect. A ferocious predator with jaws like a mechanical grab. It seems unlikely, but this animal's ancestors were among the first creatures ever to fly. But this one is not yet adult. It's a larva, and it doesn't spend all its life in the water. It has another life and another body above the surface. Early one morning, it climbs up a reed. A split appears in its skin, and a very different-looking creature begins to emerge. It has 4 lumps on its back that might perhaps ancestrally have become either gills or protective armor plates. But now they develop into something very different. Wings. it has two pairs of them. Liquid from its body is pumped down along veins to stretch them tight. As they dry in the sun, they harden. The water-living dragon has become the dragonfly, and the four-winged apparatus that it uses to get into the air is the earliest that we know. Imprints of such wings have been found in rocks that were laid down on the bottom of ancient lakes and streams. This specimen is about 150 million years old. And this wing is double that age at nearly 300 million years old. Ancient and modern wings share a structure that is strikingly similar. So today's dragonflies are amazingly living fossils that can show us how the very first flyers overcame the pull of gravity and took to the skies. Their wings are marvels of natural engineering. But to see how they lift a dragonfly into the air, we need to slow the action down. In principle, it looks fairly simple. Each wing beats down, pushing on the air below, so lifting the dragonfly up. But each beat also creates another air current that lifts the dragonfly in a very different way. And I can demonstrate it using this strip of paper to represent a wing. If I blow across the top of it, it'll rise. Watch. That is because the faster air moves, the lower its pressure. So I created a lower pressure above the wing, and in consequence, it was sucked upwards. The problem for a flying animal is to recreate that difference in airspeed. The way the dragonfly does this is remarkable. As it moves through the air, we can see that it twists its wings at different angles. On the powerful downbeat, it holds them at a slight upwards angle to the airflow. And this produces an extraordinary effect above the wing. It creates a swirl behind the leading edge, which spins the air round, increasing the speed of the air current over the top of the wing. And just a tiny increase in speed generates a significant upwards force, lifting up the wing and the dragonfly. The dragonfly can then change the direction of its wing beats to propel it forwards as well as upwards. Remarkably, a dragonfly can beat each of its four wings independently. And that enables it to perform an astonishing variety of maneuvers. It can hover. It can glide. It can even fly backwards. For maximum power, it beats both pairs together and can make really sharp turns. So the very first dragonflies were able to extend their territories far and wide. And as more insects joined them in the skies, the dragonflies had the skills to be deadly aerial hunters. The ability to fly brought great advantages to those early insects. It enabled them to find food, to escape from predators, and particularly important, to travel to new territories in search of a mate. Damselflies, like their close relations dragonflies, have remained virtually unchanged for millions of years. Mating can be quite complicated when both partners can fly, and these were among the first kind of animals that had to deal with that problem. The blue colour of this one shows that it's a male. To attract a female, a male must have something to offer her, a territory. He chooses a stretch of water that is likely to contain plenty of food for his offspring. Then he guards this territory against any rivals, until a female flies in and joins him. He must now grab her before she changes her mind, in mid-air if necessary. He uses claspers at the tip of his abdomen to grip her behind her neck. Amazingly, the pair are able to coordinate the beats of their 8 wings. They may mate in the air or choose a secluded perch where they'll be safe from predators. They then fly around the territory, laying their fertilized eggs. Flight enabled insects to invade part of the planet that until then had been uninhabited, the air. And they flourished. So, 320 million years ago, the skies thronged with flying insects. But those early 4-winged forms were destined to produce a whole range of spectacular, highly specialized flyers. The need to lay eggs in water tied the first dragonflies to streams and ponds like these. But then, around 20 million years after their arrival, a new kind of flying insect appeared with no such ties to water. Proof of their success can be found almost wherever you look, and few places more abundantly than in Borneo. The very first flyers had 2 pairs of wings. Now we're looking for their successors. One group of creatures adapted that original 4-winged design with such success that they diversified into the most numerous and widespread group of animals on the entire planet. And you can find some of the most spectacular examples down there in the rainforest. Not all insects are hunters. Some are strict vegetarians, like this one. This is the land-living equivalent of that underwater monster, the dragonfly larva. But this larva, instead of catching little fish and water fleas, munches wood pulp. The trouble is that wood pulp is not very nutritious, and this creature has to eat it for at least a year before it's this size, which is full grown. But then this larva will turn into an adult, which is equally monstrous. Emerging from beneath the ground, where it has lived and fed as a larva, is a beetle, one of the biggest in the world, the Atlas beetle. Males like this one are armed with long horns, powerful weapons with which to compete with rivals for a mate. It now spends most of its time above the ground, barging its way through the undergrowth where it feeds on tree sap and fallen fruit. This hefty, powerful creature may not look as if it could fly, but it can. At key moments in its life, it takes to the air to look for new sources of food and, of course, a female. All this burrowing and rummaging around could injure delicate flight wings, so beetles have hardened the front pair to form this pair of protective covers, and the delicate flight pair are stowed away in safety underneath. To see how the wings are folded away beneath their covers, we need to wait for takeoff. As it flaps, sprung hinges click open and the wings are stretched to their full size. The working wings create lift in just the same way that the dragonfly's wings do. And the front wings, which have now become covers, are held out to the side. And their shape does give a little extra lift, but it's clear that this is really rather a clumsy flyer. Landings can be clumsy too. And now those fragile wings must be carefully packed away beneath their covers. They're guided by a line of tiny hairs at the base of the abdomen. These grip the wings and help push them into position. The beetle does it with all the care and precision that a skydiver uses when packing away his parachute. Once in a new territory, it will stake out a fresh source of food and then defend it until a female arrives. The beetle way of life proved astonishingly successful. There are over 370,000 different species of beetle so far discovered. Unbelievable figure. So early on, the beetles managed to fly as much as they need to with just one pair of wings. And then, around 57 million years ago, came another key development in the history of flight. A new type of insect appeared, with two pairs of wings that became, in effect, huge billboards. Wings that are perhaps the most dazzlingly beautiful of all. butterflies. To create these extraordinary wings, the butterflies evolved a complex life cycle. They hatch from eggs as little worms with legs, caterpillars. But unlike many beetle grubs, caterpillars find their food above ground, where they're very vulnerable to predators. So they have evolved several strategies to accumulate all the body mass they will need to become flying adults. The first is to eat as much as they can, as quickly as they can. Many are able to reach full size in just a matter of weeks.
Of course, a little thin-skinned, fat-filled sausage is a tempting morsel for any bird or reptile. So caterpillars have to have ways of defending themselves. This one, which is the caterpillar of a lovely swallowtail butterfly, has disguised itself as a bird dropping. And if that doesn't deceive a bird, and a bird goes for it, it has another form of defense. It's emitted a rather unpleasant smell as well.
In the struggle to survive long enough to become winged adults, other caterpillars have developed other equally ingenious forms of defense. Concealed within these fluffy strands are short, stinging spikes.
And this one is armed with long spines which have really painful stings. Not only that, it has these bright warning colours to tell any potential predator that they'll be in trouble if they attack.
This caterpillar may appear to be dangerous, but it is in fact a fraud. The spines don't sting at all. It's relying on its disguise to make a potential predator think twice and leave it alone.
Or you can simply hide. These little tents have been made by the caterpillars of a skipper butterfly. Each caterpillar has started by making a circular cut in the edge of the leaf, but it's left one segment uncut so it can act as a hinge. Then it pulls over the whole segment and hides beneath to munch away at the tissues of the leaf. And if I just pull it up, there's the caterpillar.
Caterpillars that survive this hazardous stage can now build their wings and turn into adults. They undergo a truly radical transformation. Instead of shedding a final layer of skin as a dragonfly does, a caterpillar first surrounds itself with a protective shell to act as a sort of changing room, within which it dismantles and then completely reconstructs its body. After around 10 days, it emerges as a butterfly. Now fluid pumps along veins in the wings to stretch them out to their full size. And then it is ready to fly. Butterflies live on nectar which they collect from flowers. Like dragonflies and beetles, they also fly to find a mate. But the way they beat their colourful wings is significantly different.
This lovely creature has two pairs of wings, but it has in effect turned them into one. It's done that quite simply by overlapping the larger front pair over the smaller hind pair, so that when the front pair beat down, they automatically press down the lower pair. The lower pair themselves don't have the muscles to beat down, but just enough strength to return up.
A butterfly's overlapping wings, compared to the size of their bodies, are enormous, around 10 times the size of other insect wings. Because the wing is larger, each beat can generate a huge amount of lift. So, to stay airborne, a butterfly needs to flap less often than other insects. But that slow wing beat also enables it to make rapid and unpredictable changes of direction.
And that allows butterflies to fly in that zigzag, erratic way, which makes them so difficult to catch if you're a butterfly collector, or more importantly, a predator. The combined front and hind wings of a butterfly not only constitute very effective flying mechanism, they can also carry messages. In fact, they carry some of the loveliest advertisements in the whole of the animal kingdom. Like, for example, this beautiful golden birdwing butterfly from Borneo.
The butterfly's huge wings provide a spacious canvas on which to display fantastically elaborate designs. So how are these flying advertisements created? The secret lies in the microscopic structure of the wing surface. These overlapping scales, lined up like tiles on a roof, have evolved from bristles that were once tiny sensors. Some contain tiny packets of pigment that give the wings colour. Others have a complex structure which splits the light so that when viewed from a particular angle, it reflects a brilliant iridescence. There are over 18,000 species of butterfly around the world, and each has wings with their own distinctive design.
These ravishing colours and delectable patterns, of course, enable a male butterfly and a female butterfly to know whether or not they belong to the same species. And a mature adult, ready to mate, can identify a suitable partner from surprising distances.
When a male and female eventually meet, they flutter around each other in a ritual dance. Each is checking out the flying skills and wing patterns of the other. If both pass the test, they mate. The sheer size of butterfly wings might seem to condemn their owners to a slow, almost dawdling flight. But they can be much more efficient aeronauts than you might suppose.
Butterflies may not be able to fly very fast, but astonishingly, for such frail-looking creatures, they can travel for hundreds of miles in search of food.
New discoveries are revealing that butterflies make immense journeys. And one of the most exciting of these studies is taking place 7,000 miles west of Borneo in Europe. I am joining a research project in central Spain to look for one of the greatest of all butterfly travelers, the painted lady. Every spring, painted ladies appear in Spain in great numbers. But Spain is just a stopover. An international team of scientists are uncovering evidence of an astonishing journey right across Europe and beyond. This hugely ambitious project is the brainchild of Dr. Constante Stefanescu. Detailed records of when and where painted ladies appear have revealed an extraordinary mass migration.
We were able to collate a huge number of observations from more than 60 different countries and maybe 35,000 records.
Really?
Many people contributing their observations. And for the first time, it was possible to understand the general pattern of migration all year round.
By combining this wealth of data, the team are revealing a route map that spans incredible distances. And it begins in North Africa. Large numbers of painted ladies breed in Morocco over the winter, before setting out across the Mediterranean to Europe. They then follow the spring bloom north, as the plants that they and their young feed on sprout leaves and flowers. In summer, they appear in Britain and Scandinavia. But no individual butterfly lives long enough to achieve this huge journey by itself. Each step is taken by a new generation. So this painted lady in Britain is the grandchild of a butterfly that set out from Morocco. But then, in autumn, all the painted ladies vanish. Do they simply die out, or could there be a return leg to their epic migration? Searching for an answer to this mystery has given the project its most astonishing revelation yet. And it comes from a part of the team based at Rothamsted Research Institute, just outside London. The key discovery emerged from a surprising source: radar.
Our radar has a vertical pointing beam, and it illuminates a narrow column of the sky above, like shining a powerful spotlight up into the sky. And we're able to detect individual insects as they fly through that beam.
The signal is so detailed, it can even help identify the species. And during the autumn disappearance, the radar picked up large numbers of painted ladies. They weren't dying out, they were on the move, and they were flying at astonishing heights.
What we found was that, in fact, the painted ladies were highly abundant at heights of 300, 400, 500 meters above the ground.
At this great height, they were invisible to observers down below. This explained their disappearance. But the butterflies had their own very good reasons to travel at such altitudes.
One of the benefits of flying at 300 or 400 meters above the ground is that the wind speeds there are much faster than they are at ground level. So the insects are able to get a lot of assistance from the wind and travel much faster than they would under their own powered flight. And we see these painted ladies traveling at 50 or even 70 kilometers an hour.
As well as measuring the phenomenal speed of their flight, the radar also revealed its direction. They were heading south. So where were they going? The astonishing answer came from Constanti's far-flung network of observers, and the crucial piece of data was gathered in Africa.
Some expeditions in Africa in October, November have shown that there is a huge arrival of butterflies at that moment. So by the end of the summer, the newborn butterflies in Europe start to migrate way back to Africa.
Really?
Yeah.
A final generation riding on high-altitude winds makes an immense journey of up to 3,000 miles to West Africa in just a matter of days. Observers on the ground and radar in the air had found proof of an amazing migration cycle.
Just in 1 year, the whole cycle is made, and is the succession of these 6 generations moving about 5,000 kilometers in one direction and 5,000 in another direction.
This migration is in fact the longest made by any insect on the planet so far discovered. But that raised another question. How did each generation know which direction in which to fly? The Rothamsted scientists once again set out to find an answer by tracking the behavior of painted ladies much closer to the ground.
This is our flight simulator experiment. What we've done is we've tethered our butterflies to a very fine rod, and we put them inside these flight simulators. They are rigged up to the computer, and the butterflies are free to turn, and as they're turning, we're recording that turning, and we can actually draw out the flight path that they would have taken if they were free flying.
The barrel blocks the butterfly's view of the surrounding scenery, removing any possible distractions. The only reference point they have is the sky above. Remarkably, the butterflies consistently choose a common direction.
These are the flight headings, so each spot is one individual butterfly and the overall direction that they went in. So you can see that on average my butterflies were flying south. What we found when we put the lid on the simulator so they couldn't see the sky is, as you'll see, they didn't know which direction to go in. They weren't able to maintain the southwards heading.
Rebecca concluded that their ability to choose this heading must depend on the one thing they can see in the sky above: the sun.
Actually, the sun is a really good cue. It's very predictable in its movements across the sky, and butterflies will be flying in the middle of the day when it's warm, when the sun is out, and the sun will be in the south at that time of day. So that's a really clear cue for the butterflies to know which way is south.
This inbuilt compass allows painted ladies at high altitude to select a wind that's heading south, and so hitch a free ride on the long return journey all the way to Africa. Some insects face a very different challenge, not flying long distances, but flying in the dark. A light trap can attract some of the most remarkable of these nocturnal flyers. Moths. Moths probably evolved to fly at night to avoid predators. Their eyes are adapted to low light, but they also use a second highly developed sense: smell.
This is a male moon moth. Moths overlap their two pairs of wings in just the same way as butterflies do. And this particular moth is very special. It has an extremely short life. It will only live for a week. It won't even feed. Its only object is to find a female. And it does that with these remarkable feather-like antennae. The female emits a particular characteristic scent, and with those antennae, the male can sense it from as much as a mile away. It then takes off and flies upwind until eventually it finds the source.
Moths, with their combined front and rear wings, are also excellent flyers. Some live longer and so need to fly to find food. This sphinx moth's favourite food is nectar. It can even hover as it drinks.
So by overlapping their two pairs of wings, butterflies and moths have become very competent flyers. But there's one group of flying insects that has changed the back pair of wings into something quite different. Something that enables them to perform the most extraordinary aerial gymnastics.
For the final chapter in our story of flying insects, I'm returning to London. The urban jungle and its human inhabitants provide plenty of shelter and food for a particularly adaptable and numerous kind of insect.
Thank you very much. Thank you. An inviting meal like this one will, I'm quite sure, very soon attract a flying diner that is one of the most remarkable of all insect aeronauts.
It is, of course, a fly. This particular kind, a blowfly, occurs all over the world, and its ancestors have been buzzing around for at least 250 million years.
Flies are so common, we tend to dismiss them as just irritating pests, but their flying abilities are truly remarkable. Watch what happens if I try and swap this one with the menu.
Slowing down the action by 40 times, we can see how astonishingly agile flies are. It makes its escape in the time it takes me to blink my eye. The ability to twist and turn at such high speeds and so evade enemies has made flies the global success that they are.
They are the jet fighters of the insect world, and they owe their maneuverability not to the shape of their wings, nor the power of their muscles, but to a set of highly advanced flight sensors.
A fly has its own version of a fighter pilot's instrument panel, providing constant updates on speed, altitude, and direction of travel. A fly gathers this flight data through its eyes, and these are among the best in the business. They can process visual information around 10 times as fast as our own eyes. But in high-speed maneuvers, even a fly's eyes struggle with one crucial piece of flight data: the angle of its body in the air and the way it changes. information that a human pilot would get from an instrument based on a gyroscope. And that is essential if you're going to pull off a stunt like this one. Fortunately, flies not only have eyes to guide them.
They also have a second and even more remarkable set of sensors, one that is derived from that original four-wing design.
A fly only has a single pair of wings. The rear pair have been converted into something else. A tiny club-like appendage known as a haltere. This surprisingly sophisticated organ alerts the fly to changes in the position of its body in the air. As the fly takes off, each haltere begins to beat up and down, and so fast it immediately becomes a blur. But in slow motion, we can see that it swings back and forth like a pendulum. To understand how the haltere works, we need to track its movement in a mid-air roll. The weighted tip of the haltere has a kind of moving inertia, so that it remains on the same swinging path as the fly banks. Now, the angle between the body and the haltere changes, and the base is put under strain. This triggers sensors which register the roll. The fly can then adjust its wing beat to correct any imbalance, however extreme. New studies into a second remarkable use of the haltere signal are taking place at London's Imperial College. In the Department of Bioengineering, experts are studying blowflies to see if their natural flight mechanics can improve the performance of man-made flyers like this drone.
Flies are incredibly maneuverable. And if you look at their performance, one chasing another one, it's really hardly any other animal that can match this sort of aerodynamic performance.
Holger has devised an experiment to investigate an intriguing connection between a fly's halteres and its other key flight sensor, its eyes. A tiny motor simulates a series of high-speed mid-air rolls. The way the fly then reacts is recorded on a specialist camera which can replay the action in slow motion.
As you can see, if you look closely, the head of the fly is maintained level. The body is rotating, and to maintain a level gaze, they have to counter-rotate the head.
Keeping the eyes level is vital if they're to gather accurate flight information, and the halteres have been identified as the crucial sensor that makes this possible.
Visual system alone would just be too slow. That's where actually the halteres come in. The halteres are extremely fast in terms of their responses, and their immediate signals that are then sent to the neck motor system and to the flight motor system, they are the first really to compensate for any disturbances. And if that has happened, the visual system is perfectly well situated to cope with the rest.
So flies lost a pair of wings, but gained an extraordinary new flight sensor that made them the most advanced flyers in the insect world. Flight has enabled the insects as a whole to become an astonishing global success. There are twice as many insect species than there are of all other animals put together. Theirs is a remarkable evolutionary story that spans over 320 million years. From the first four-winged creatures that emerged from the water to the armour-plated beetles which colonised land away from water. The butterflies with their huge colourful wings and the stunningly skillful aerobatic flies.
But skill may not be enough. Sometimes sheer size counts. The insects had the skies to themselves for around 100 million years. But then a new group of animals appeared, animals that could build bigger bodies. And they were to lift the techniques of flying to even greater heights.
As our journey through time continues, we encounter the extraordinary pioneers of a new wave of larger flyers. Monstrous winged reptiles. Strange feathered dinosaurs whose ventures into the air led to the birds. And a group of mammals that conquered the pitch black of the night. The bats.